Okay, so that was mostly something I wanted to show you to lead into other things, which we will get back to in a minute. Let's see. I've got all these different PowerPoints this time. But I couldn't finish a course on software engineering without talking a little bit about Moore's Law. And because it is perhaps, embodies the main thing that's been driving our entire field of computer science and software engineering and computer engineering and everything else for the last 60 or so years. And I'm sure you've all probably heard the term Moore's Law, and you may or may not have any idea what it means, so let's just spend a minute on that. So Moore's Law is the number of transistors on integrated circuits doubles approximately every 2 years. So what's an integrated circuit? Well, it's the software course, not hardware course. But it's a chip. It's a little computery thing. And what's a transistor?
If you put a voltage in it, it'll either keep that voltage through or...
Right. So it's sort of a switch, right? You can turn things on or off. And with transistors, you can build more complex logic that will then do things like ands and ors, or add numbers together, or play video games. So it's sort of the building block of almost all computer stuff. So, so here's just a picture from 1969. This was one of the original early integrated circuits, and it did 108,000 instructions per second. Pretty darn fast. So that KHZ, kilohertz, a hertz is means one thing per second. So if you're a kilohertz is 1,000 things per second, and this is 108,000 things per second. What are those things? Well, like add numbers together or move data around in memory. Fairly recent, the Intel Core i7, 306 gigahertz. That's a lot faster, right? A gigahertz is a billion, so we're basically going from 100,000 to a billion, so that's a lot faster. And it's also got a lot more. I couldn't find the number of transistors, but it's billions. So anyway, those are just pictures. Obviously, larger than life-size pictures. So why is it important if the number of transistors doubles? Well, the transistor stays at about the same size. So if you put twice as many on, they're closer to each other, and that means they're faster, because a lot of what takes time is moving electrons and such from one point to another point. If you make those points closer to each other, they go faster. Also, they're more powerful. They can do more things. They can add more numbers, and they can, there's power in other ways. There's the cost stays about the same per transistor. Per integrated circuit. Not exactly, but the cost is about the same. In other words, a few $100s. So if we can get a lot more transistors on for the same cost, then they're faster, and the price has gone down. And that's really nice, right? That doesn't happen in most fields, right? Automobiles over the last 50 or 60 years have not gotten half as expensive and twice as powerful every 2 years, as you may have known. And same for just about everything else. Books are about the same. But somehow, for reasons that are really beyond this class, it is happening in computer technology. So it's good to know that Moore's Law is named after a real man named Gordon Moore, who in 1965 published in a journal called Electronics an article called Cramming More Components onto Integrated Circuits, using the technical term, cramming. And Gordon Moore went on to found Intel, which I know you've heard of. And here's the picture from his original 1965 paper, where he took 5 data points from 1959, 62, 63, 64, 65. Notice that they were kind of linear and extrapolated. So he's writing this in 65. The dashed is my guess, or his guess. Okay? Now, this is a straight line because the x-axis is kind of the normal x-axis. Each centimeter is a year, or whatever it is. But this is the logarithm of the number of components. So remember, if you double a number, the log goes up by 1, right? If we go from 100 to 200, the log of 100 is half the log of 200, okay? So even though it looks like a straight line, it doesn't mean that from 1962 to 1963, it just went up like from 3 to 4. It went from 2 to the 3 to 2 to the 4, which is twice as much. Okay, so I know some of you are totally familiar with log charts, but some of you probably never understood them and still don't. So that was Moore writing in 1965. As it turned out, he was right. And here's a chart that starts in 1970 and shows various, for the most part, Intel processors. And you can see it's still a pretty straight line. Here, rather than having the log, we show the actual number. So this is 10,000, which is 10 log 3, 10 log 4, 10 log 5, 10 raised to the 4th, to the 10 raised to the 3rd, 4th, 5th, 6th, 7th, 8th, 9th. So you can see the straight line thing is pretty reasonable. And here's, since this was just to 2000, here's some more data up through 2010. And with red is Motorola chips and blue is Intel chips. So this isn't something that's just, one company or something. And it's still pretty much a straight line, right? Still, once again, logarithmic here. So it's kind of amazing. And then here's another way of looking at it, is the hardware has gotten faster, but how about the software? So here's what I've done. I superimposed on the same chart as before, Microsoft operating systems, Windows 3.1, 95, 98, Windows NT, Windows XP, and over here, how many millions of lines of code, also on a logarithmic scale. So you can see that as the chips got faster, Windows got larger at pretty much the same rate. And of course, that's just Windows, but it turns out people have done this for other pieces of software. And in general, it's the same thing. So computers have gotten faster, software has gotten bigger, software has only gotten faster for the most part because the underlying computer that's running on has gotten faster. It's not that software is necessarily much better than it was 20 or 30 years ago. But what's the main limiting factor in all this? Not hardware. Software grows. What doesn't change? There's been no perceptible increase in human intelligence over the last 50 or 60 years. Okay, so that's kind of a big picture thing. I'm not going to directly relate to software engineering, but everything in software and hardware is sort of driven by this Moore's law. Henry Samueli, who I know you've heard of because he didn't found, but he funded the engineering school, which is the Henry Samueli Engineering School, and he runs a very large chip-making company on campus. He gave a talk about his predictions for the future of these things a month or two ago on campus. And if you ever hear about Henry Samueli giving a talk on campus, I would say, go see it. He's interesting. And rich. So I'll just finish this up with something I've been afraid about all quarter long is that maybe you guys are suffering from PowerPoint poisoning. Normally I don't use PowerPoints in this class, and I don't know if you can believe that, but this one was so large, and I thought if I write on the board, people in the back won't be able to see it, so we're doing PowerPoint. You'll recover over the summer.